Welcome to the Digital Communication course. In today's session, we will do PSD of line code scheme and pulse shaping. This is the lecture 7. In the previous lecture, we have done the line coding, different type of line coding techniques. Now next is PSD, that is power spectral density of the line codes. Now what is PSD? PSD is the function which gives distribution of power of a signal at various frequency. We are plotting the power with respect to frequency. Now a line code that is used for the data transmission of a digital signal over a transmission line. This process of coding is chosen to avoid the overlap and distortion of signal such as inter-symbol interference. Now the function which gives the distribution of power of a signal at various frequency in frequency domain. We are plotting the power with respect to frequency, that is known as your power spectral density. Power with respect to density. For PSD calculation of line code, we have 3 steps. In first step, we have to calculate the Fourier transform of the pulse. The pulse that we are transmitting, suppose we are transmitting 1 with a positive pulse and 0 with 0 voltage in the case of unipolar. Now first we have to calculate the Fourier transform of the pulse that we are transmitting. Now line coding that convert over binary data into digital signal. Now we have to do the Fourier transform of this pulse. Second, to calculate the autocorrelation of the pulse. Now what is autocorrelation? In the previous lecture also we have done this autocorrelation function in statistical averages. Autocorrelation function, that is you want to find out the similarity between the two signals. Now we are relating the two processes and we have to find out the relation between them that we have done in the random processes. So we have to find out the autocorrelation of the pulse and Fourier transform of the signal. After calculating the Fourier transform and autocorrelation, we applied the Wiener-Khinchin theorem to find out the PSD of the signal. The PSD of the signal is 1 by TB XF square summation autocorrelation function and the Fourier transform of this TB. We have to take the Fourier transform of this autocorrelation function and apply this formula to find out the PSD for line codes. Now PSD is very important parameter for line codes that can be controlled by the line coding technique or the pulse shaping techniques. Now in the next slide we will calculate the line coding. We will calculate the power spectral density PSD for different line coding techniques such as unipolar, polar, bipolar, Manchester. Now we will calculate the PSD for different kind of this line code. By this PSD we can compare this line code also, which is having the least power spectral density, which having the highest power spectral density. Now see, this is the some numerical part how to calculate the PSD. Now PSD can be calculating using the autocorrelation function. First we have to find the autocorrelation function. A digital signal is represented by a pulse having a Ts equal to Tb and duration of the one symbol multi-level signal is Ts by 1 by Tb. Now PSD depend on the pulse shape used. The pulse that we are used, suppose in unipolar we represent 1 bit as a plus voltage and 0 bit as a 0 volt. But in case of the polar we represent 0 bit as minus 1 volt, right? In bipolar we have 3 level, one will be represented as a positive 1 or minus 1. We are changing the polarity alternately, that is the alternate mark inversion, and 0 will be represented as a 0. Now let us calculate the power spectral density of a digital signal. Now here you can see this is the formula for the power spectral density. In the previous slide I have write this PSF is the power spectral density that will comes in the frequency domain F. FF is the Fourier transform of the pulse. the pulse we are using here is rectangular pulse 0 to TB. You have to find out the Fourier transform of this, that is denoted by FF. This term, the mode of FF square divided by TS. TS the sampling time for the per bit is equal to TB, right. Summation RK. RK is the autocorrelation function of the pulse. This is the pulse that we are using for unipolar, polar, bipolar. The autocorrelation function RK e की power minus का j 2 pi k FTS, where the k limit is minus to infinity, where Ft is the Fourier transform of FFF. Now, first we will find the autocorrelation function, then we will find the Fourier transform of the pulse. Now, this is the formula for find out the autocorrelation function. RK, whereas summation an plus k and I pi, whereas I limit is vary from 1 to I. Now, first we have taken one signal an, another is an plus k, and pi is the probability of that event. The autocorrelation function of the data an and ark are the level of the data pulses. Now, an and ank plus is the data level of the pulses. If you are taking this pulses, this is the plus 1 data level for 0 data level. So, 1 should be, if we are taking an and ank plus, then 1 should be different from another. If the k value is 0, then an and an will be the same, right, and p is the probability of having that an data level. Now, see here we are calculating the PSD for polar enhanced signaling. Now, for polar, one bit is represented as plus a, for 0 bit is represented as minus a. Now, we are calculating the autocorrelation function for the same. Now, an and an plus k are the level of the pulse at the end and nk plus of the symbol. Now, see here, if we put k equal to 0 here, if k is equal to 0 here, then the autocorrelation function of an and an will be the same level we are taking, because we are equating k equal to 0 here. Now, an I pi is the probability of that event. Now, an is means we are if taking 0 0, right, or we can take 1 1, or for 0 0 we are having a voltage minus a, and the for 1 1 is plus a. Now, the square of this an, like if this is an, this is an, sorry for this, these are the over bit and the voltage assigned for this bit, that is an. We have to take the same voltage here, that will give you an square, that is a square and a square. Now, probability of getting this a square is 1 by 2 and is the 1 by 2, right. Now, here we are applying the formula. If we take the bit is 0 is transmitted, the voltage assigned is a square and the probability is 1 by 2. Here the a square 1 by 2. If the 2 bit is transmitted the same 1 1, the probability, the voltage assigned is a square and the probability is 1 by 2. Here we are taking the a square 1 by 2. After combining them, we are getting the autocorrelation function, that is a square, right. The autocorrelation function that will come out at k equal to 0, that is a square. Now, when the k is not equal to 0, we are calculating the autocorrelation function. Now, if the k is not equal to 0, we have the 4 cases of the bits like 0 0 0 1 1 0 1 1. The an can be and an plus k, it can be 0 0 0 1 1 0 1 1. These are the 4 cases when the k is not equal to 0 and the voltage is assigned, it is minus a plus a plus A minus A plus A plus A. After multiplying these two values, because in the formula we have an plus k, we are multiplying these two voltages, we will get A square minus A square minus A square and A square. Now, this is the four possible outcomes of when we are not taking k equal to 0, when we are taking k not equal to 0. The probability of getting this 4 event, that is 1 by 4 each. Now, we are multiplying this because we have to multiply the voltage by this pi. A square by 1 by 4 multiply minus ka A square multiply 1 by 4 minus A square multiply 1 by 4 minus A square multiply 1 by 4. The total autocorrelation function will be come out equal to 0. When k not equal to 0, the autocorrelation function is 0. When k equal to 0, autocorrelation function is A square. Right. So, we have calculated the autocorrelation function. Let me rub it. The autocorrelation function is come out is A square and 0. Now, another part is we have to find out the Fourier transform of the pulse. The pulse we have taken is plus A volt for 0 to TB. We can also draw this pulse in a shifted version TB by 2 minus TB by 2, and this is A. If you want to take the Fourier transform of this pulse, you can apply the direct formula of Fourier transform from minus TB by 2 to TB by 2 limit, and having the amplitude A and e की power minus का j omega t, you can write omega by 2 pi f respect to dt. After solving this equation, you will get the Fourier transform, that is f, and it will come out sin pi f TB by pi f TB. We can equate this term, we can replace this term by sync pulse also, sync FTB. This is the Fourier transform of this pulse. If we take the Fourier transform of this pulse, that is sync FTB TB is the Fourier transform of the pulse. Now, we are applying this Wiener-Khinchin theorem. The formula for the Wiener-Khinchin theorem is FF mod square TS. TS is our sampling time, that is equal to TB. Now, it will come out A square by TB sin pi f TB upon pi f TB square. Now, see here, this A square is coming from the autocorrelation function, right, when k equal to 0, and this is coming out from this Fourier transform of this pulse. Now, this is the PSD for polar NRZ. Similarly, we will find out the PSD for unipolar, PSD for bipolar. Now, for the unipolar, bipolar, the Fourier transform of the pulse is remains same, only the autocorrelation function will change. So, you can find out the same step will be followed to find out the autocorrelation function. The step will remain same, means FFF will be the same come out for this unipolar and bipolar. So, in next slide we will not calculating the PSD for bipolar and unipolar, you can do it by yourself, and I will show you the values the PSD for unipolar and bipolar. Now, the for unipolar PSD will come out A square by TB by 4 sin pi f TB upon pi f TB square 1 plus 1 by TB delta f. Now, delta f is our impulse signal which having value 1 at f equal to 0. Now, this is the PSD for unipolar, and for the polar it will come out A square TB sin pi f TB by f TB. Now, see in this case You can see in this case you can compare these two PSD. Now see, polar PSD is higher as compared to unipolar PSD. Now that will, because in polar PSP autocorrelation function, it will become 0 for k not equal to 0. Now for the next slide you can see is the PSD for unipolar RZ, and the for polar RZ it is a square TB by 4, and the for the Manchester it is a square TB sin pi FTB by 2 square pi FTB by 2. So we can compare the PSD of with different line coding technique. In this you can see polar NRZ which is having the highest PSD as compared to others. Now the PSD for unipolar NRZ, that is a square TB by 4, and the for PSD for RZ it is become very less, that is 16, a square TB by 16. Now next is our pulse shaping. Now what is pulse shaping? When the digital data are transmitted through a band limited channel, dispersion in the channel causes an overlap in time between successive symbol. Like if we are transmitting one pulse, now this pulse will be spread out beyond its time period TB to 2 TB. When digital data are transmitted through a band limited channel. Now what is band limited channel? When we transmitted this pulse, the channel that we are using which is having a very low bandwidth. Due to this, the pulse will be dispersed in the channel, causing an overlap in between the successive symbol. So it will overlap with the alternate symbol, or you can say successive symbol. The channel carrying these pulses never have enough bandwidth required to ensure the preservation of the shape of the pulse. This form of dispersion is known as inter-symbol interference. Now over symbol that we are transmitted through pulses that will overlap due to the dispersion, that is a serious problem in pulse shaping that should be controlled. The pulse shaping techniques enable perfect reception in the absence of noise. Now by using pulse shaping technique we can reduce this ISI problem. ISI is inter-symbol interference due to the band limited channel over pulse is dispersed from its time period TB to extending to 2 TB. Now in electronic and communication, pulse shaping is the process of changing the waveform of the transmitted pulse. The purpose is to make transmitted signal better suited to purpose of the communication channel, typically by limiting the effective bandwidth of the transmission. By filtering the transmitted pulse, this way the inter-symbol interference caused by the channel can be kept controlled. If we change the pulse, instead of sending this rectangular pulse, we can change the pulse shape, we can control the ISI, that is inter-symbol interference. In RF communication, pulse shaping is essential for making the signal fit in its frequency band. Now this is the advantage of pulse shaping technique. We can control the PSD by line coding technique and pulse shaping. PSD is the very important parameter that we have calculated for unipolar, polar, bipolar. Now this PSD can be controlled by the line coding technique and the pulse shaping techniques. Pulse shaping is more important than the line codes. Main purpose of the pulse shaping is to eliminate or reduce the ISI in the communication. Main reason for ISI is due to the band limited channel or multipath fading. Now what is the cause of the ISI? That is a band limiting channel. Now see in details what is ISI. Inter-symbol interference. Inter-symbol interference occurs when a pulse spread out in such a way that interfere with the adjacent pulses at the sample instant. Suppose we are sending multiple data 1, 0, 1. Now over pulses will be spread out like which having a duration of 0 to TB. Now it will be taking the duration minus TB to TB, that is 2 TB is the dispersion of the pulses or spreading out the pulses due to the band limiting channel that will cause the ISI. Now ISI arising due to this channel, frequency limited, that is called the time unlimited, that is called the ISI. Time limited, that is the bandwidth unlimited. Now this is the diagram of a when we are transmitting a pulse through binary data, then we are transmitting through pulses, that is AK pulses. Now here we are using the transmit filter, channel filter, receiver filter. These two filter causes the ISI. We have to remove this filter by a certain filter so that the ISI can be removed. Now here you can see in this slide the spreading of the pulses is taking place. One is spreading out like this way and 0 is spreading out in negative domain, and this again one is spreading out this way, and here you can see the overlap of the adjacent pulses. Here you can see the overlap of the adjacent pulses that will cause the ISI. Here you can also see sequence of bit. We have to transmit 101. Instead of sending 101, we are receiving the 111. That will call the ISI. In this slide is also explained the ISI. If the rectangular multiple level pulses are filtered improperly as they pass through a communication system, they will spread in time, and that pulse of each symbol may be smeared into adjacent time float called the intersymbol interference. Here you can see this 1 and 0 is data is represented as spreading of this pulse into like this, because the Fourier transform we have taken of this rectangular pulse is come out sync pulse. It's spreading in the terms of sync pulse. Here you can see at this point cause the intersymbol interference, because 0 to TB we are having a 1 value, and for 0 we are having to show this 0 volt, but at this point we are getting some value here that will cause the problem in the receiver end. Similarly in the case also. Now this is the Nyquist first method for 0 SI. Now how it can be controlled ISI? Now this can be controlled by the Nyquist first method for 0 SI. If we use this kind of filter, is means we have to use the transfer function or impulse response, that is HET sin pi ft by pi ft, where Fs is 1 by Ts. Instead of sending the rectangular pulses, we will send the pulses in terms of sync pulses like this. For one bit we are using this blue one, for the another bit we are using the red one. The most of the energy contained in the top of the level of this sync pulses. And if we take the Fourier transform of this pulse, that will give you the rectangular pulse shape diagram. To control the ISI, we will use this type of transfer function, that is known as Nyquist first method for 0 ISI. Now in the last I diagram. What is I diagram? I diagram is measure of evaluating the quality of the received digital waveform. Now in order to judge the ISI impact, we will use the I diagram. I diagram level reveal the impact of ISI and the noise. I diagram can also give the estimate of achievable BER, that is the bit error rate. Now here you can see the amount of ISI can be seen on an oscilloscope using an I diagram or I pattern. Now here you can see this is the duration of the pulse, that is TB. Here you can see this is the distortion impact. If it's extension beyond TB, then the ISI will be there. This height, vertical height, will give you the noise margin. And the vertical eye opening or noise margin is related to the SNR or thus the BER. The vertical eye opening of this eye diagram is give you the SNR, that is the signal to noise ratio, and BER, whereas horizontal eye opening will give you Okay. And horizontal eye opening relates the jitter and the sensitivity of the sampling of the instant. So that's it for the today lecture. Thank you.